day at GE. And then we'll have a meeting at school on Thursday. So our question comes from your homework. The homework questions is burning paper a chemical change? Marley said yes. She wrote down paper and oxygen. Paper is composed of cellulose, which is C6H10O5. This would be cellulose. And then we have oxygen. Ash. What is ash and gases going to be? Anybody know? This has oxygen, so anytime you see oxygen as a reactant and a reaction, it's going to be a combustion reaction. So you're going to get like CO or CO2 in water. Now your automobile produces CO without the catalytic converter. So you'd have to investigate to see what you're actually getting in the reaction, whether it's predominantly CO or CO2. But all combustion reactions are going to end up producing a carbon-oxygen/water product. That's how you know it's
is a fundamental that is summarized as the law of defined properties. The law of
You're off task. Let's just tell Brady he's off task.
The law of definite proportion states that the compound is always composed of the same elements in the same proportion by mass, no matter how large or small the sample. The mass of the compound is equal to the sum of the masses of the elements that make up the compound.
Amari, thank you for following along. Good job. All right, so we have two CO molecules here. This would be carbon what? Monoxide. Di means two. Good. So this is carbon monoxide. The carbon dioxide, you have two oxygens. Makes sense? Di is two. So they're saying the law of definite proportions, the mass of the carbon in one compound is going to be the same as the mass of carbon in another compound. That's the law of definite proportions. It's true with water as well. So if you had like H2O, two water molecules, the oxygen masses are going to be the same in both. And hydrogen as well. Masses are not going to change per water molecule. That's what defines differences with the isotopes of carbon, because you have different numbers of neutrons, which gives a different mass, but it's not going to be enough to designate it as being a different element. The mass will still be close enough to be designated as carbon. Identify whether we have cocaine or, let's say, baking soda when the police pull over a suspect, because you're going to have different proportions of a substance in there. And that's why you have to do a lab analysis. So here you can see that we have a proportion of carbon has a mass of 12, so we know we have one of them. You have to know the masses in order for any of this to make any sense. That's why we broke things down from mixtures and determined substances, and then we wanted to break them down to elements to find out what the masses are. Once you know that, then you can kind of figure out what your unknowns are. There are a lot of unknowns out there. We're still finding new species. There are places in the ocean we've never been. So if we take 12 divided by 12, that's going to equal 1, because we know that the mass of carbon is 12. Does everybody see that? Now we know that the mass of oxygen is 16, so if we divide that by 16, we know we have a 1. So the mass ratio comparison here is 1 to 1. There's 1 carbon per oxygen. Now, fortunately, we were able to break this CO2 down, and we know that it does have oxygen, but it has a different mass associated with it. CO2 is very different than CO. It has different physical and chemical properties. Is everybody clear? You have to test for this to know that they're different. Now, once you know that they're different, then you have to do things to help promote this. We want more of this being made in our environment. Why do we want more CO2? Plants like it. Plants prefer this over this. Like there's certain foods that you prefer and you're going to want to eat those, and that would be CO2 for plants. So we know that the mass of oxygen is 16, so we divide 16 by 32. What does that equal? 2. 2. So this equals a 1 to 2 ratio. This is very important as far as the law of definite proportions. This helps us understand that the mass is going to be the same for the oxygens. And then that gives us a 1 to 2 ratio. Law of multiple proportions. So we have multiple proportions happening here of the oxygen. That's what's going on. It's more than one. 2 unknown compounds Two unknown compounds are tested. Compound 1 contains 15 grams of hydrogen and 120 grams of oxygen. Compound 2 contains 2 grams of hydrogen and 32 grams of oxygen. So they want to know, are the compounds the same? So are these compounds the same? Now looking right off, we break this down. The mass of hydrogen's 1, mass of oxygen 16, so we have a 2 to 2 ratio. We simplify that to HO. What is this? Peroxide. You ever seen the brown bottle? Yeah, so peroxide is written HO. Peroxide. So that's how you know it's peroxide and not water. Water's H2O. Everybody clear? Now this over here, you've got like a 15 to 7.5. Now you cannot have a 0.5, so you're going to have to multiply this times 2. So you're going to have 30 of these, and what's 7.5 times 2? 15. So you're going to have H30 and O 15. So that's going to simplify to what? What's 15 divided by 15? What's 30 divided by 15? 2. So you're simplifying this to H2O. You've got to simplify to the simplest whole number ratio. So this is a ratio of 2 to 1.
Particles which gave each kind of matter its unique characteristics was all but obvious.
On this table. It was the lightest element. So it was the lightest element he could find, so then he divided it by itself. It wasn't 1, it was just the lightest one he could find. And then he divides everything else by that, and he creates this table.
How do you weigh an element?
He used a balance, like he had a scale. We don't have it here anymore, but like a seesaw.
Oh, like that one where it's like you're weighing it against something else.
Yeah, like a seesaw. You ever been to a park and you've been on a seesaw?
How does he know it's there? Yeah.
Well, you can put hydrogen in a glass container and capture it.
But how do you capture the hydrogen in?
Well, if you have a bottle, right, full of water, and you put a tube in there underwater, and when you do a reaction, the tube can transfer the gas into the bottle and push out the water. So you can capture gases. They were knowledgeable of that at this time. Yeah, so I mean it's technical, but it can be done. Good question. You go to the periodic table, you find the mass of nitrogen, which is new, introduced. But Kristen, we should know the mass of oxygen, which is 16. We've talked about that since the beginning of the period. You divide the two, you get a 2 to 3 ratio. This is the pattern that is consistent. It's very important to be able to identify in case you're charged with a crime you didn't commit. Down the road, you have a suspicious white powder in your automobile. The police pull you over, and they think that it is, let's say, cocaine. And they go back and they test it in the lab, and they find out that it's sugar. This happened just recently. So they thought it was originally cocaine because they can't taste test it. They have to test it in the lab to know for sure. But the law of definite composition allows us to be able to test these things and know for sure. Because the mass of carbon here is going to be the same as the mass of carbon here. It's called the law of definite composition. Now we have isotopes that have a different number of neutrons, but the mass is still going to be close enough to indicate that it is carbon.
Compare the relative amounts of any items or substances. The comparison can be expressed using numbers separated by a colon or as a fraction. With regard to law of multiple proportions, ratio expresses a relationship of elements in a compound.
When we're working with the law of multiple proportions. Anybody? Annika? What must we know for working with the law of multiple proportions? Look, we're building on the law of definite proportions. Did you write this note down? Law of definite proportions state that the mass of carbon-12 must be the same in both CO2 molecules. It's the law of definite proportions. So what must we know to be able to figure out the law of multiple proportions? We need to know the masses of the substances, specifically the elements. Okay? So what's the mass of carbon? Okay, the mass of carbon is 12. It's right here, mass of carbon is 12. Now you have to go to the periodic table to find the mass of oxygen, right? So it's 16. If you look on the periodic table, mass is 16. Right. And here we have a carbon, so its mass is 12. And we have two of them here, so what's 16 times 2? 32. Does everybody see that? Now, so we go back, we know the mass of carbon is 12. We know the mass of 16 is 6, or the mass of oxygen is 16. So this is a 1-to-1 ratio. Carbon monoxide is a 1-to-1 ratio. So we're looking at the ratio of the substance that we have. This is 1-to-1, carbon to oxygen. This is 12. This is 16. So this is a 1-to-2 ratio. So in the law of multiple proportions, it's really all about the figure 3.2, which states the mass ratio comparison. It's all about the mass ratio comparison. That is how they got this 2 right here. If you're wondering how they got the 2, it's coming from the mass. Now let's take a look at a problem in the book. Problem number, obviously he's building on Lavoisier, but which person gets Dalton's attention? Which work? Democritus. So Democritus is kind of the influence also for Dalton. So is Lavoisier. And he reads about it and he starts working with his atomic structure, with the atom. And he comes up with this table in 1803, Dalton's Table of the Elements. Now, did Lavoisier have a table? Yeah, they both had tables. What was different about them? Most likely the mass of the oxygen. You can see how oxygen has a 7 there. They struggled with the mass of oxygen. Why? You might know why they struggled with the mass of the oxygen? Dalton's Table of the Elements, 1803, with oxygen a mass of 7. I've got it listed up here at 1805. He's got oxygen with mass of 5.5, right? So oxygen was the struggle. Why was oxygen the struggle? Because they didn't know it was bound with water with 2 hydrogens. They didn't know it was diatomic, that is, most of your elements like hydrogen and oxygen are diatomic. They exist bonded with itself together. So there are 2 hydrogens bound with oxygen. They didn't know that. They just thought it was like a 1-to-1 ratio. So that's why you see a difference in the 7 here compared to the 5.5 up on the board there. It can make a big difference when you start looking at the mass of your lightest element. So what's the lightest element? Yeah, it's 1. Now, where did they get the 1? How'd they come up with 1? Did it just equal 1? Yeah, it becomes a standard. So if it was like you have a balance, and let's say on the balance you have something else, and it ends up being like 0.5, well, you divide 0.5 by itself and you get 1, and that becomes your standard. So hydrogen became the standard because it was the lightest element, so they gave it a mass of 1 just by dividing by itself. And then you divide everything else by hydrogen, and you can figure out how many parts oxygen you have of hydrogen. So there are 5.5 parts hydrogen in oxygen. Make sense?
Heavy gases did not settle out of nature, and simple experiment confirmed his suspicions regarding partial pressure.
Okay, so Dalton is building on the work of who? Lavoisier and who else? Democritus, so we talked about that yesterday. John Dalton became an English school teacher at what age? What? Raise your hand, I couldn't hear you. Yeah, 12. He was like, I think in the 7th grade when he became an English school teacher. And what grade did he become the principal? Or how old was he when he became principal? So he became principal of the school at around 18. They don't ever talk about him being principal. They just talk about him being an English school teacher because he was probably just so young when he was doing it. Did he ever go to the university? No, he never graduated from a university. So why didn't he graduate from a university? Lily? Why didn't John Dalton graduate from a university? He didn't have the resources, didn't have the finances. Back then you had to pay for it. There weren't a lot of scholarships. Unless your father, your parent graduated, that could get you in the door sometimes like Mendeleev. So he didn't have the resources to do that. So what he did, he got into labs. He got into the library and labs with just special permission to do that. Now, he's building on the work of Democritus. And Democritus, we talked about yesterday, his thinking was ex materia, right? So the atom, you couldn't take half of it. Now, in today's science, we've gone away from ex materia and we've gone to ex nihilo. Even though emptiness has never been proven. If you look in the lab, we've never been able to form emptiness. So it's really a philosophical concept. And we've never been able to take something and pull it out of nothing. We've never been able to take something and turn it into nothing. We've never been able to form something out of nothing. So that's never been proven. So there's a lot in the Big Bang that's never been proven. Are you following me? If you show that it's proven, come back and show me, and then I'll be more accepting of it. So the question is, well, why are we, promoting that? What's the reason for that? Well, if you look at the links that I posted, there are some reasons that are given. Ex nihilo, the biggest one, is that ex nihilo and proclaim that we can be assured that there's no evil in the universe. So evil is basically the primary reason why ex nihilo is being promoted. They don't want to view God as being evil. So, if everything turns back into emptiness, like the heat death. I mean, I'm not freaking out at the Catholic Church over this, because at least they're being honest. They're promoting the heat death, which the universe eventually turns back into emptiness. Whereas this gentleman up here is not really explaining that to you, that everything will eventually turn back into nothing, so there's no eternal word. So the question is, why are they promoting it again? Because evil, right? They don't want to think that God is evil. But when you're looking at ex nihilo, what are you eliminating? What does ex nihilo eliminate? Yeah, free will. Write this down. With ex nihilo, there is no free will. So if somebody's talking to you about free will, well, in ex nihilo, there's no free will. Because there are no opposites. If you eliminate like free will, then there can be no evil, really. Because you didn't have the free will to choose. I mean, free will is what is associated with what is good or what is bad. You have the free will to choose to do something good. You have the free will to choose to do something bad, right? So really, evil is associated with free will. You could say love is associated with free will. There are 5 love languages. Anybody know what the 5 love languages are? All of them are associated with work. What? 5 love languages would be...
French.
No, I'm talking to like the language of love, which would be gifts, acts of service, time, encouraging words. What else? Huh? Gifts, acts of service, encouraging words, time, touch. Very good. Thank you, Lily. Yeah, so touch you got to be very careful with, because it has to be appropriate touch. So those are all work, right? You have to work to do that, to show that. The important part about the law of multiple proportions concerns the mass ratio comparison. It helps us determine the subscript, which is right here, for the substance. Lavoisier, it says here, the prior work of Lavoisier. Lavoisier is very important. He's considered the father of chemistry. But what he does, he disproves Aristotle. Aristotle, prior to Lavoisier, was the dominant thinker. Lavoisier says, no, air is composed of oxygen. It's a mixture. He actually names oxygen. So he's a huge person for us in science. Lavoisier, he like kills Aristotle. That is his thinking. So, Lavoisier. Now, Dalton builds on Lavoisier. And Dalton's getting his thinking from who? Democritus. Because remember, Democritus proposed the atom, and the atom is still true today. Right? Now, as we continue on with
data, that is, concept of individual particles, which gave each kind of matter its unique characteristics, was all but obvious.
Okay, so yesterday we learned about Democritus, Aristotle, and what was the other guy's name? Heraclitus? Yeah, Heraclitus. Now, we come across Lavoisier. Who did Lavoisier disprove? Lavoisier is considered the father of chemistry, so who did he disprove? That was the predominant thinking during his time. Aristotle. Yeah, so Aristotle was disproven by Lavoisier. Lavoisier basically proved that air was a mixture. And then he named oxygen. He said air was composed of oxygen and other things as well, but he was the one who named oxygen. So there's a big shift when Lavoisier comes out and says, well, Aristotle's wrong, and he's able to provide data to support it. So no longer does everybody think earth, fire, air, and water anymore. They're now thinking along the lines of who? Starts with a D. Democritus. So Lavoisier is studying Democritus, the idea of the atom. What does atom mean?
Cannot break.
Yeah, can't take half of, right? Now,
Oh my god. I feel like 27's gonna drop. Oh no!
get on there. 26.